Okay, so I want to look at this as wavelength is getting smaller. Oh, there we go. Okay, so like I said, typically we would read it from this way to this way, and that would be as wavelength gets larger. But I want to go from this way to this way, okay? So as we're moving from here and we're moving toward the origin, wavelength is getting smaller. So let's denote that here. Okay, so we have on here, as we move from this way to this way, wavelength's getting smaller. So as we move from here to here, I see that my intensity is increasing. And I see that for both of these. This blue line's starting to go up, this black line is starting to go up. So both sets of physicists, both classical physicists and modern physicists, thought that as the wavelength got smaller, I would see an increase in intensity. So that's true. Where everything messes up is that if I follow this blue line, classical theorists thought that that intensity would just continue to get bigger and bigger and bigger. But that's not what really happens when I reach this point right here. And I'm darkening this out because I want you, on top of that graph, to write UV. This is where the part of the electromagnetic spectrum, this is where the ultraviolet region starts. When the ultraviolet region starts up here, I actually see a decrease in intensity as the wavelength gets smaller. So at long wavelengths, I see that as wavelength gets smaller, at the longer wavelengths, as it's starting to get smaller, intensity increases. But once I get to the UV category, there was a scientist named Planck who found once I get to UV, intensity doesn't increase anymore. It actually starts to decrease. It actually starts to decline. So that's what Planck found, and that's actually what we still know true today. So classical physicists could not figure out an explanation for this. It wasn't until this guy named Planck came along and started to question, okay, well, why do I see that at UV, give me just 1 minute, guys. Okay, why do I see that at UV, the intensity starts to go down? I don't understand. So at this point, this guy named Planck, he starts to say that this has to happen because electrons must be holding a certain amount of energy. And so this is where we get this phrase, a quantum of energy. And when we say quantum of energy, quantum just means like a very specific amount of energy. So quanta or quantum just means that something can hold only a very specific amount of energy. So just like my cup of tea here can only hold up to the top of this before it starts overflowing, it's the same thing as like an electron can only hold a certain amount of energy, and then otherwise that energy is not going to be absorbed or emitted. It's just the electron can't hold it at all. It can only hold a certain amount. Just like my cup of tea can only hold a certain amount of tea. Okay? So it's kind of what an analogy for quantum or quanta. Why do we call this the UV catastrophe? The reason that scientists called this the UV catastrophe was because classical physicists truly believed that as we go from radio waves to gamma rays, that gamma rays would have the most intense type of radiation. They would have the most intense type of energy. We would see that, and not so much energy, but it would be energy that we could see. It's energy that we can actually visualize, and that's not true. So it wasn't until Planck came along, Max Planck, and this was in 1900, wasn't until Max Planck came along and he said that he looked at this, he did several experiments, he came up with this graph, and he found classical physicists are wrong. This was huge. He called this the UV catastrophe because at the UV radiation, a UV spectrum, UV category in our spectrum, that's where the intensity actually starts to decline. It starts to decrease as the wavelength gets smaller. So it's a UV catastrophe because UV category in the spectrum is where we see things all starting to turn around and the intensity actually decreases. Okay? Let's move to slide number 6. And this is just talking about Planck. So we're still talking about the same stuff, but we're just now focusing on Planck. In slide number 6, it says that Planck realized that the ultraviolet catastrophe goes away if we assume that the possible values of energy of electromagnetic radiation are not continuous, but rather they come in little packets. So what that means is, like what we just said, electrons can only hold a certain amount of energy. Just again, like my Starbucks cup can only hold a certain amount of tea. I wish it was unlimited. I wish I could be like a classical theorist and think that the amount of tea that's in my cup is going to continue to get more and more and more. However, there's a limit. So that's what Planck is trying to come up with. Planck found through all of this that electrons can only hold a certain amount of energy. And we call that energy little packets or little pockets of energy. We just call that a quantum of energy. So this is where quantization comes in. A quantum of energy, again, just a very small, certain amount of energy. Discrete, in your book they always say like a discrete amount of energy, and all that means is it's just a certain amount of energy. Just a particular amount of energy that we know an electron can hold. Okay, so Planck came up with a mathematical relationship, and this relationship is that the energy that something holds, the energy that an object can hold, is found by a formula. And you'll see here that that formula says E equals N times H times F. Okay, well you know what E stands for, and that's energy. And you know that F should stand for frequency. Okay, so our F just stands for frequency. H is actually just a constant, and I wrote that constant down below on that same slide on number 6. So you'll see here, this H is actually called Planck's constant, and Planck's constant is 6.63 times 10 to the negative 34th, and that's joule seconds. Where will you be able to find this on your AP test? At this point, you should be yelling, in the front of the book, in the front of the book. And you'd be correct. So on your AP test, on your multiple choice part, on your, on your free response part, you will have that constant for you in front of the book. So you will always be given this number. Okay, so H is Planck's constant. I think they even tell you that it's Planck's constant. So H is Planck's constant, and that's equal to 6.63 times 10 to the negative 34th joule seconds, okay? And I can find the amount of energy that an object has by a formula. And that formula is E equals N times H times F. What does the N mean? And that's what you're like, I don't know what this N means. And I see on the side, on that slide number 6, it says N equals 1, 2, 3, etc. So E equals N times HF. I want to go back